We've learned a little bit about probability. Now we're going to talk about a related topic called expected value. Probability we can think of as organized thinking about random events. Now we're going to try to understand what happens on average when there are values attached to the random events. And that's a bit vague, so let's look at an example. You're going to roll a 10-sided die and you get money depending on what happens. If you roll a 1 through 5, you get $0. If you roll a 6, 7, 8, or 9, you get $5. And if you roll a 10, you hit the jackpot and win $100. So what is the probability that you win nothing? Well, 50%, 5 chances out of 10. What's the probability that you win $5? Well, 40%. It's 4 out of 10 ways of winning a $5 bill. And the probability of winning $100 is 10%. But how much do you win on average? If you play this game over and over again, how much would you expect to be ahead on average per roll, per turn? Some people are tempted to just say that there are three things that could happen. You could win 0, 5, and 100. So you just average those three and you get $35. I hope that seems a little strange to you, because that would tell you that the answer didn't matter, didn't depend upon how likely each of those outcomes was. It would be the same if you got $100 8 times out of 10 and 0 and $5 just once each. That can't be right. You have to pay attention to how much you win, but also to how likely those events are. So the way to think about it is to play the game 100 times and ask yourself what happens. If you imagine playing the game 100 times, then 50 times you're going to win nothing, 40 times you're going to win $5, and 10 times you're going to win $100. Now, if you actually played this game 100 times, what would happen wouldn't be that exactly, but it'd be pretty close. That's sort of the ideal outcome according to the probabilities. So the total amount of money you win in 100 plays would be, well, 50 times you get 0, 40 times you get 5, 10 times you get 100, and that's 1,200, adds up to 1,200. So $1,200 in 100 plays is an average of $12 per turn. And in general, you can just multiply the probabilities times the value of each outcome and add them up. So instead of asking yourself what happens if you play 100 times, you could just take 0.5 times 0 plus 0.4 times 5 plus 0.1 times 100, and you get that same number, 12. And that's called the expected value. It's the long-term average. So if you played this game over and over again, then on average you'd get about $12 per turn. So by the way, that means that if someone said, hey, you can play this game and it'll only cost you $10, it would be worth it in the long run. If you could play this game over and over again for $10 each, that'd be worth it. On the other hand, if they said, hey, here's a chance to win $100 and you've got lots of chances to win at least 5, you can play this game for only $13, well, it wouldn't be a good deal. So the general formula is you take the probability of each of the outcomes times the value, the number attached to it, and add them up. P1, V1 plus P2, V2 plus et cetera, et cetera. Let's look at another example. You drive to work. 40% of the time it takes you 30 minutes, and 60% of the time it takes you 20 minutes. How long does it take you on average? Well, we'll just use the formula. 40%, 0.4 times the value 30, plus 60%, 0.6 times the value 20, and do the calculation, and that's 24 minutes on average. And that's not just the average of the two numbers 30 and 20, which ought to make sense because it's 20 minutes drive more often than it's a 30-minute drive. Let's look at another example. You roll a 6-sided die. If you roll a 1, you win $1. If you roll a 2, you'll lose $3. If you roll a 3, you win $5. If you roll a 4, you lose 7. Roll a 5, you win 9. Roll a 6, you lose 11. Well, the expected value of each of those rolls is 1/6. Sorry, the probability of each of those rolls is 1/6. So the calculation for expected value looks like this. 1/6 times 1, because you win 1, minus 1/6 times 3. Why minus? Because that's losing $3. Plus 1/6 times 5, minus 1/6 times 7, etc. And you get -1. So on average, you lose $1 every time you play, on average. Played this game over and over again, you'd expect to be down about $1 per turn. One last example, a little more complicated maybe. You flip a coin 3 times. Count the number of heads you got. Square the number, and that's how much you win in dollars. So if you got 3 heads and no tails, you win $9. Got 1 head and 2 tails, you win $1. Now, to find the probabilities of each outcome, we have to spend some time. We can't just, it's not easy to know what that is. How are we going to find the probability of getting 3 heads, 2 heads, 1 head, or no heads? Well, we're going to make a systematic list of all the things that can happen when we flip a coin 3 times, and we're going to keep track of the order. Well, here they are. You could get heads, heads, heads. The first 2 flips could be heads and the last one tail. The first one heads, the second one tail, the last one heads, etc. There are 8 things that can happen. One of them has 3 heads, 3 of them have 2 heads, 3 of them have 1 head, and 1 of them has 0 heads. So if we keep track, we could flip 3 heads. It has a probability 1/8. There's only one way you can get 3 heads, and the payoff is $9. You can flip 2 heads. The probability is 3/8, and the payoff is $4. You can flip 1 head. The probability is 3/8, and the payoff is $1. Or you can get no heads. Probability 1/8, the payoff $0. So the expected value is 1/8 times 9 plus 3/8 times 4 plus 3/8 times 1 plus 1/8 times 0 equals $3. So on average, if you play this game over and over, you'll be $3 ahead. And so if someone offers to let you play it, if you pay them $2 just to play, it's worth it. If they ask you for $3.20 to play, it's not worth it. So this is a small introduction to a very important topic. And one place this sort of comes up in real life is with lottery tickets. If you look at the very small chances of winning a lottery compared to even with the high payoff, most lottery tickets, most $2 lottery tickets, the expected value of playing the lottery is close to -$2. Your chances of winning are so slight that the big payoff doesn't outweigh the long-term risk of what happens. And for that matter, if you go to a casino, same thing. Almost all the games have a negative expected value for you. People do win, but more people lose, and that's how casinos make their money, off of the negative expected value to you, the positive expected value to them.